Between December 1983 and January 1984, an Arctic air mass descended across the continental United States and remained in place for weeks. Winter infrastructure in North America was designed to operate within established thermal ranges based on historical norms. Systems maintained functional capacity through routine cold snaps lasting days. The assumption was that severe cold would pass before reserves depleted or thermal limits were exceeded. Winter temperatures across the central and eastern United States typically ranged from 20 degrees Fahrenheit to 40 degrees Fahrenheit in December and January. Infrastructure systems, power generation, water distribution, transportation networks were engineered with cold tolerance margins based on this baseline. Natural gas delivery, electrical transmission lines, and water mains operated continuously through seasonal temperature drops. Equipment functioned within rated limits. Heating demand followed predictable curves. Reserve capacity existed for multi-day cold events that occurred several times per decade. Engineering standards assumed recovery periods between cold episodes. The system was built for intermittent stress, not continuous exposure at thermal extremes. In late December 1983, a southward extension of the polar vortex pushed Arctic air masses across the Canadian border into the northern United States. The displacement was not anomalous in mechanism, but in persistence. Cold air originating above the Arctic Circle moved through Alberta and Saskatchewan, crossing into Montana, North Dakota, and Minnesota. Surface temperatures dropped to levels normally confined to polar regions. The air mass did not retreat. Standard atmospheric mixing that would normally moderate such intrusions failed to develop. By December 22, temperatures in Bismarck, North Dakota registered negative 35 degrees Fahrenheit. The cold front continued southward without weakening. The jet stream adopted a deep meridional trough pattern over North America. Instead of zonal west to east flow that would transport the cold air eastward and allow moderation, the pattern locked in place. The trough extended south into the Gulf states. Warm air could not push northward. The configuration held for multiple weeks. Each reinforcing pulse of Arctic air followed the same pathway, maintaining surface temperature depression across 2/3 of the continental United States. Meteorological models showed no breakdown mechanism. The atmospheric block persisted through normal cyclic disruption periods. Cold air continued to flow south along the eastern slope of the Rockies. On December 22, 1983, temperatures across the northern plains dropped below negative 30 degrees Fahrenheit and remained there. Chicago recorded negative 27 degrees Fahrenheit on Christmas Eve. By December 24, every state east of the Rockies reported temperatures below freezing. The South experienced readings 30 to 40 degrees below seasonal averages. Atlanta measured 6 degrees Fahrenheit on January 21. Florida citrus regions dropped below 20 degrees Fahrenheit for consecutive nights. The rate of temperature decline exceeded infrastructure adjustment capacity. Equipment designed to handle gradual cooling faced instantaneous thermal shock. Wind chill values, while not affecting infrastructure directly, indicated heat transfer rates that accelerated all thermal loss processes. Temperature records fell across hundreds of reporting stations simultaneously. The cold was not localized but continental in scope. Minimum temperature readings persisted day after day with no moderating trend. Overnight lows became daytime highs. The normal diurnal temperature cycle compressed into a narrow band of extreme cold. Forecasts projected continued Arctic flow for the remainder of January, with no pattern change visible in long-range models. Heating load across the eastern interconnection increased by 25 to 40% within 72 hours. Natural gas consumption spiked as thermostats called for continuous operation. Electric resistance heating in regions without gas service pushed demand to winter peak records. Utilities activated reserve generation capacity designed for brief peak periods. Load duration curves exceeded planning parameters. Demand remained at emergency levels day after day. No overnight relief occurred. Baseload plants operated at maximum continuous output. Peaking units designed for 4-hour duty cycles ran for weeks. Fuel stockpiles began drawing down faster than delivery schedules anticipated. Coal-fired plants faced fuel handling problems as coal piles froze into solid masses. Conveyor systems designed for free-flowing material could not break apart frozen chunks. Natural gas-fired generators encountered pipeline pressure drops as residential demand diverted supply. Some plants experienced combustion efficiency losses in extreme cold air temperatures. Equipment rated for operation to 0 degrees Fahrenheit encountered conditions 40 degrees colder. Auxiliary systems failed. Cooling water intake structures froze despite flow. Instrumentation gave erratic readings outside calibrated ranges. Plant availability factors dropped as units tripped offline. Reserve margins collapsed across multiple regional grids simultaneously. Grid operators watched real-time demand exceed available generation. Emergency protocols designed for brief contingencies became sustained operational states. The power system was entering territory beyond its design envelope. High-voltage transmission lines contracted in extreme cold, increasing tension on support structures. Conductor sag calculations assumed minimum temperatures that were exceeded by 20 to 30 degrees. Aluminum and steel components experienced differential contraction rates, causing mechanical stress at connection points. Insulators became brittle. Lines carrying maximum current for extended periods operated at thermal limits, while ambient temperatures removed all cooling margin. Transformer loading exceeded nameplate ratings. Mineral oil viscosity increased, reducing cooling effectiveness. Substation equipment experienced failures unrelated to ice or wind loading. The stress came from sustained operation at temperature extremes with no recovery interval. On January 10th, rolling blackouts began across multiple cities. Detroit implemented load shedding affecting 400,000 customers. Milwaukee, Chicago, and Cleveland followed. The outages were not weather damage events, but controlled failures to prevent total system collapse. Grid operators manually disconnected circuits to balance generation shortage against demand. Each disconnection lasted 30 to 90 minutes before rotating to another sector. Some areas experienced multiple outages per day. The thermal mass of buildings provided limited protection. Indoor temperatures dropped 10 to 15 degrees during each outage cycle. When power restored, demand surge from heating systems restarting created secondary stress on the grid. Operators managed a continuous crisis with no resolution path visible. The cold showed no signs of breaking. Generation capacity could not be added. Demand could not be reduced below survival heating levels. The system operated in managed failure mode. Municipal water systems experienced pipe failures as sustained freezing penetrated below burial depth. Ground frost reached depths exceeding design parameters in northern states. Soil that normally provided thermal insulation froze solid. Frost lines extended 6 to 8 feet deep in some locations, well beyond the typical burial depth of water mains. Cast iron water mains dating from early 20th century construction fractured under thermal contraction. The material became brittle at extreme low temperatures. Thermal stress exceeded tensile strength. Service lines to individual buildings froze despite normal operation during previous winters. The duration of exposure exceeded the thermal capacity of soil to protect buried infrastructure. Repairs could not be executed in minus 20 degree Fahrenheit conditions. Ground was frozen solid. Excavation required specialized equipment. Exposed repair crews faced life-threatening cold exposure. Broken pipes were isolated and customers lost service. Some areas went without running water for days. Fire suppression capacity degraded in multiple municipalities simultaneously. Hydrant systems froze. Water towers experienced ice formation that reduced capacity. Treatment plants struggled to maintain operations as chemical feed systems and clarification processes encountered temperature-related failures. The water distribution network, designed as a continuous closed system, fragmented into isolated functional segments separated by frozen sections. Urban areas faced the prospect of losing water service not from contamination or supply shortage, but from the physical failure of the delivery infrastructure under thermal stress. Diesel fuel gelled in truck fuel tanks and locomotive systems despite winterization additives. Fuel blended for winter operation was formulated for temperatures to -20 degrees Fahrenheit. Ambient conditions reached -40 degrees Fahrenheit across major freight corridors. Paraffin wax crystals formed in fuel lines, blocking flow to engines. Rail operations slowed as track components contracted beyond tolerance limits. Steel rails shortened measurably. Gaps at expansion joints closed, then reversed, creating buckling risk. Switch heaters could not maintain operation in sustained extreme cold. Electrical resistance heating elements designed to prevent ice accumulation were overwhelmed by heat loss to ambient air. Pneumatic switch systems froze. Signal systems experienced failures. Freight movement decreased by 40% across northern routes. Highway bridge deck temperatures dropped to -40 degrees Fahrenheit, causing pavement and joint failures. Concrete experienced thermal contraction cracking. Expansion joints seized. Steel bridge components contracted, creating stress concentrations at connections. Interstate corridors experienced closures not from snow, but from pavement fractures and structural concerns. Tire blowouts increased as rubber lost flexibility at extreme cold temperatures. Vehicle starting failures stranded motorists. Battery capacity dropped to fractions of rated amperage. Engine oil viscosity increased beyond pumpability limits. Commercial transportation networks designed for cold weather operation found themselves unable to function at temperatures 30 degrees below their operating envelope. Supply chains dependent on just-in-time delivery began experiencing cascading delays. Steel mills in Pennsylvania and Ohio shut down blast furnaces as natural gas supply was diverted to residential heating. The furnaces required continuous high-volume gas feed to maintain internal temperatures above 3,000 degrees Fahrenheit. Reduction in gas pressure made sustained operation impossible. Shutting down a blast furnace was not a routine event. Restart required weeks of controlled heating. The economic loss extended far beyond the shutdown period. Automotive plants in Michigan suspended operations when building heating systems could not maintain minimum assembly line temperatures. Paint curing required specific temperature ranges. Adhesive bonding failed below thermal thresholds. Workers could not sustain productivity in buildings where indoor temperatures dropped to 40 degrees Fahrenheit, despite heating systems operating at maximum capacity. Heat loss through building envelopes exceeded heating system capacity. Chemical facilities faced process failures as reaction vessels could not maintain required temperatures against heat loss to extreme ambient conditions. Exothermic reactions that normally sustained themselves became net heat losers. Temperature-sensitive catalysts deactivated. The shutdowns were not weather closures, but operational impossibilities. Industrial processes requiring specific thermal conditions could not function. Economic activity across the manufacturing sector dropped measurably. Each day of extreme cold extended the shutdown duration as restart procedures required controlled warming that could not begin while ambient temperatures remained below critical thresholds. The industrial base of the northern United States entered an involuntary hibernation, waiting for atmospheric conditions to permit resumption of normal operations. Livestock mortality increased across cattle-raising regions in the Great Plains and Midwest. Animals and outdoor feedlots faced wind chill conditions below -60 degrees Fahrenheit. Cattle physiology could not maintain core body temperature against such heat loss rates, even with maximum metabolic output. Shelter structures provided limited protection against sustained extreme cold. Three-sided windbreaks reduced wind chill but did not address ambient temperature. Water sources froze despite heating elements. Livestock went without water for extended periods. Feed consumption increased, but animals could not metabolize sufficient calories to maintain body temperature over multiple weeks of exposure. Caloric intake required to offset heat loss exceeded digestive system capacity. Estimates placed cattle losses in the tens of thousands across multiple states. Poultry operations experienced ventilation system failures as air handling equipment iced over. Chickens in commercial production facilities require specific temperature ranges. Ventilation systems must remove moisture and ammonia while maintaining warmth. The systems could not achieve both objectives in extreme cold. Buildings either froze or accumulated toxic gas concentrations. Citrus crops in Florida suffered freeze damage across hundreds of thousands of acres. Citrus trees tolerate brief freezes, but sustained exposure below 28 degrees kills living tissue. Multiple consecutive nights of freezing destroyed fruit still on trees and damaged trees themselves. The agricultural impact totaled billions in losses. The biological limits of livestock and crops had been exceeded by atmospheric conditions that persisted beyond survival thresholds. Emergency services faced call volumes that exceeded response capacity. Medical emergencies related to cold exposure, hypothermia, frostbite, carbon monoxide poisoning from improvised heating increased by orders of magnitude. Ambulance services encountered mechanical failures. Emergency vehicles experienced the same fuel gelling and starting problems as civilian transportation. Response times extended. Hospitals saw surge admissions at the same time staff could not reliably reach facilities. Heating system failures in medical buildings created secondary crises. Fire departments responded to structure fires caused by overloaded electrical circuits and improvised heating methods while hydrant systems remained frozen. Firefighting in sub-zero temperatures created immediate icing. Water spray froze on contact. Equipment became encased in ice. Firefighters faced life-threatening exposure. Each emergency response generated additional equipment failures and personnel exposure risks. The cascade effect accelerated. Power outages caused water system failures. Water system failures degraded fire suppression. Fire risk increased due to heating system overload and improvised heat sources. Transportation failures delayed emergency response. Each system failure created stress on remaining functional systems. The redundancy and reserve capacity built into critical infrastructure assumed isolated failures, not simultaneous multi-system degradation. Emergency management protocols designed for discrete events could not address a sustained continental-scale thermal crisis. Authorities faced the reality that response capability was becoming the limiting factor, not the nature of individual emergencies. In late January 1984, the jet stream trough began to weaken. Zonal flow resumed across the Pacific. Warmer air masses moved eastward. Surface temperatures across the affected regions rose above freezing for the first time in weeks. The atmospheric configuration that had locked Arctic air over the continent dissipated. By early February, temperatures returned to seasonal norms. The cold wave ended not through gradual moderation, but through pattern replacement. The aftermath involved assessment of infrastructure damage that would require months to fully catalog. Pipe networks needed systematic pressure testing to identify freeze damage. Electrical equipment that had operated beyond ratings required inspection and replacement. Transportation infrastructure needed repair of pavement and structural damage. Agricultural losses were counted. Industrial facilities began restart procedures. Official temperature records documented the event. Bismarck, North Dakota recorded -60 degrees Fahrenheit. Chicago saw 12 consecutive days below zero. Over 100 million people experienced temperatures below zero. The cold wave established benchmarks for duration and geographic extent. Engineering analyses identified equipment and design standards that required revision. The event demonstrated that infrastructure could encounter atmospheric conditions beyond its operational envelope, not through isolated extremes, but through sustained exposure at levels just beyond design thresholds. The failure mode was duration, not peak intensity.